Nitrogen dioxide, a prevalent chemical in acid rain, has been historically hard to detect, but now a promising new method may prove otherwise. Find out this week on Basic Chemistry. Welcome to Basic Chemistry, the show where we take scientific literature and transduce it to a frequency everyone can enjoy. I'm your host, Benjamin.
And I'm your host, Micah, and today we're covering photoactivated, mixed, in-plane, and edge-enriched P-type molybdenum disulfide flake-based nitrogen dioxide sensor working at room temperature. When it comes to the environment, most are aware of the threat that pollution poses. A common misconception is it's solely from carbon dioxide emissions, but few realize that gases like nitrogen dioxide and nitrogen monoxide also have a large impact on the environment. Nitrogen dioxide most notable in its ability to form acid rain.
Accessible detection of nitrogen dioxide is critical for environmental field research, but options have been hindered by large response and recovery times and a need for high temperature. Molybdenum disulfide semiconductors have been on the radar of hazardous gas detection research due to its high surface area for gas interaction and informative band gaps. Previously studied methods have shown moderate success with nitrogen dioxide, but at the cost of long response and recovery times.
Recent studies have asserted that sulfur vacancies and imperfect molybdenum disulfide flakes have enhanced gas molecule interaction, showing that a manipulation of active sites in molybdenum disulfide is a promising path in the detection of nitrogen dioxide. So, a group of very talented researchers took a shot at it in the hopes of developing a highly sensitive, selective, and reversible sensor with functionality at room temperature.
In case you got lost along the way, basically, being able to conveniently detect pollutants is really important, and a group of talented researchers potentially found a new way to detect nitrogen dioxide, a pollutant known to contribute to acid rain, in a way that is relatively convenient as compared to previous measures.
P-type molybdenum disulfide flakes were synthesized on a silicon dioxide and silicon substrate. This all was within a modified chemical vapor deposition system where argon gas flow was maintained at the gas inlet of the larger quartz tube that contained the smaller tube with an end closed off by the substrate, as well as molybdenum trioxide powder and sulfur powder.
The synthesis of molybdenum dioxide was detected with an imaging spectrometer. Specifically, this studied the Raman spectrum and photoluminescence of molybdenum dioxide flakes formed. A diffractometer analyzed the structure and phase of composition of the flakes. Nitrogen dioxide gas concentrations sensing was tested under three conditions: room temperature, 125 degrees Celsius, and room temperature with UV light. Gas sensing measurements of resistance, response time, and recovery time were performed for four concentrations of nitrogen dioxide at room temperature and 125 degrees Celsius. Across both temperatures, trials containing the most concentration, 500 parts per million, showed lower resistance but significantly higher response time for room temperature. The lowering of resistance alongside an increase in concentration can be attributed to an influx of nitrogen dioxide withdrawing more electrons from the molybdenum disulfide.
The increase in response time is a direct result of simply increasing the amount of molecule present to interact with the molybdenum disulfide surface, but was not observed in higher temperatures because heating induced electron hole pairs for nitrogen dioxide to quickly adsorb. So, nitrogen dioxide responds quickly to the current approach but is not recoverable at room temperature.
A study of various gases followed, because sensitivity in the previous study increased as concentration increased. The highest concentration from that trial, 500 parts per million, was used. The highest change in resistance was observed in the nitrogen dioxide by a large margin. The response time for nitrogen dioxide was remarkably less than its pollutant rival, carbon dioxide, revealing high sensitivity to nitrogen dioxide in the presence of other gases. Resistance measurements for 10 parts per million of nitrogen dioxide were replicated 10 times, showing confidence in the detector's capabilities. The high specific sensitivity was observed for other gases, demonstrating a high selectivity for nitrogen dioxide.
Because no recovery at room temperature occurred, a trial with the sensor illuminated under UV light was carried out with 10 parts per million of nitrogen dioxide. Using UV illumination, the sensitivity increased, the response time decreased, and the sensor observed full recovery. With the UV light at room temperature, the increased sensitivity to the nitrogen dioxide concentration may be significantly larger than without the UV light because UV illumination likely created new active sites on the molybdenum disulfide flakes from the release of oxygen that had been adsorbed previously.
The UV light generated photoelectron carriers like electrons and hole pairs in the flakes, and the oxygen was desorbed from the molybdenum disulfide flakes and adsorbed to the molybdenum disulfide film, thus creating new active sites on the flakes. Nitrogen dioxide interacted and attached to these sites at room temperature with UV light illumination, much better than at 125 degrees Celsius, because nitrogen dioxide was released from the molybdenum disulfide flakes more frequently at a higher temperature. Therefore, decreasing nitrogen dioxide's concentration and the sensor's sensitivity to it.
Based on the graph between charge transfer and adsorption energy, we see the sensitivity of the molybdenum disulfide to nitrogen dioxide more so than dihydrogen, carbon dioxide, dihydrogen sulfide, and ammonia. The nitrogen dioxide is more likely to hold to the molybdenum disulfide flakes. The adsorption energy for nitrogen dioxide is very high at the top of the molybdenum disulfide, top of the molybdenum atom itself, and at the top of the molybdenum sulfur bonds.
Though dihydrogen, carbon dioxide, dihydrogen sulfide, and ammonia all do transmit adsorption energy, it is not nearly as high, and the charge transfer also is significantly less than that of molybdenum disulfide, providing evidence that the sensor is sensitive to nitrogen dioxide. Overall, this high energy makes the nanoelectronic device significantly faster, even at room temperature. In conclusion, the study provides experimental evidence that the utilization of a photoactivated mixed-in plane and edge-enriched P-type molybdenum disulfide flake-based approach provides highly selective, sensitive, and fast-responding sensor for detecting nitrogen dioxide.